Hi, welcome to the Vacuum Forming Labs. My name is Rav and I'll be conducting this lab on behalf of Buckingham. So today, first thing we'll look at the risk assessment and then I'll introduce the lab activity, what vacuum forming is, and then we'll actually do the vacuum forming in the lab, and afterwards we'll do some question and answers. So first things first, the risk assessment. Anything you do in labs at Northumbria should have risk assessment attached to them. So for this one, we'll be doing vacuum forming, which involves heat and electricity. So we have risk of fires, burns, and electric shock. So some of the measures we have taken to reduce these risks is not leaving the machine unattended, so it could cause fires, not overheating the plastic, and only using handles to operate the machine and not touching it from anywhere else. There's also the risk of burning your hands while touching the material or the molds after being heated, so do not touch unless the temperature is below 50 degrees Celsius. And also there's a risk of electric shock. The machines have been pad tested, and technicians do inspect them from time to time, and we'll also give it a good look around before starting the experiment to see if there are any loose wirings. So, vacuum forming is a type of thermoforming, and it's a general term used for forming a plastic sheet, which is usually thermoplastic, using heat and pressure. First, the sheet is clamped down firmly, and heat is used to soften it. When it's heated up, it becomes more malleable or formable. When it's heated up to a desired temperature, then the vacuum is used to suck out the air, forcing the material onto the mold. And then after that's done, to prevent it from sticking to the mold, air is blown back into it to separate the formed sheet from the mold. Vacuum forming is best suited for shell type geometries. They are usually thin mold, and they have a generous radii, that means they're smooth, they don't have any sharp edges, and flowing contours. So generally the ratio of the total mold surface to flat area should not exceed around 3:1, and the ratio of depth to width into a cavity should not exceed around 1:1.5. And also generous corner radii are desired. If possible, they should be at least 4 times the material thickness. Following these guidelines ensures that you get a really good part. And next, we'll head over to the lab and continue the rest of the activity. Before we start, we should mark 60mm intervals horizontally and vertically around the sheet. Then join these using a ruler or a straight guide to form a grid. This will help you later to calculate the thickness after vacuum forming. More on this later. Once you have drawn the grid on one of the sheets, keep it safely until it dries. If you want, you can do this on all other sheets. These are the 2 molds we'll be using today. The top one is made out of high density foam and the bottom one from ceramic. Both of these have distinctive features and will perform differently under vacuum forming. We'll carry out 3 formings with the top mold at 150, 180, then later at 170 degrees Celsius, and then another one with the bottom mold at 170 degrees Celsius. Hi, so we'll be using this machine for our vacuum forming today. First we'll be using this mold, and we'll try 150 degrees Celsius, see how it forms. Then later on we'll do the same mold with 180 degrees Celsius, and we'll see what the difference is. So a few things before you start. This is the heat bed, so make sure it's always behind and it's locked, and you are wearing your PPE. This machine does not require you to wear safety glasses. And yeah, so we'll have a look at what to do. So first you need to open this, make sure it's unlocked, take it back fully, make sure it's stable so it doesn't fall on you like that. So to place the mold, we just need to keep it in the center. Then you're going to load your piece of material in there. So there's a correct way to load it. When you load it up, make sure it covers the whole area of the vent. If you leave gaps like that, what's going to happen is that air is going to seep through and you're not going to get a perfect vacuum, and the process will fail. So make sure you load it up fully, close it properly, and clamp it down. So now it's probably tight. Have a look around, see if it's properly sealed, because you don't want anything to seep through. When you have the air to seep through, you need a perfect vacuum. You need to create a vacuum. And then when you go to, after you're done loading, you can click run. And then pull this forward, which will start the heating process. Now, it will take a while to heat, but unfortunately this machine does not tell you the proper temperature, so you need to, from time to time, push it back and check the temperature. Also, make sure you don't heat it up to the boiling point of the material, because you end up with a hull. So we'll be using this to check the temperature. It's got a laser pointer, and you point at wherever you want to check the temperature, and make sure you don't aim it at anyone's eyes. So from time to time, just open it, and that's 57 degrees. So it's still not done. So we push this bit, check the temperature, which is right. So we push it all the way back, and quickly, without wasting any time, bring it forward up like that, lock it, and start vacuuming. And then when it goes through, you press stop vacuum and release. And that's it. So if you don't release it, it's going to stick to the vacuum as it cools. So after you've released it, push this down, lock it, and before you touch it, have a look. So it is below 50 degrees, so we cannot touch it. I'll lock it, lift it up, and take it out, and then check the mold temperature. It's 55, so we can't touch it, so we just have to wait until it cools down. Still no air weight. Yep, and so yeah, so now it's safe to touch. So that's our first mold, and as you can see, it does have some defect. It doesn't look a lot like the mold. So we'll try this again at 180 degrees Celsius and see how it goes. Same process, and this is now ready. Same process. Close. Have a look. Close it and wait. So we did 4 vacuum formings, 3 with the high density foam mold and 1 with the ceramic mold. And the high density foam mold is this one and the ceramic one is this one. So the high density mold we did at 3 different temperatures. It was 150 degrees Celsius, 180 and 170. The first one at 150 was the one with the grid we drew. You can see over here the grid has deformed, and we'll use this later on to calculate the new thickness. So at 150 degrees we did not get a faithful reproduction of the shape. Over here you can see it did not form well, even the depth here did not come out well, and even the sides, the corners. And the 180 degree one did start to perform well. You can see over here it has drawn it deeper, but it was too warm and the material was more malleable, formable, and it was drawn too deep over here and it pierced, and the vacuum, well, there was no vacuum then at that point, so it did not form well. You can see the shape, it's not what it should be. And if you look at the one at 170 degrees Celsius, it did fairly well. I think it's the best one out of all the 3 temperatures. You can see here it drew it to a desired depth, but we did have some faults like this. That's called webbing, and we'll have a look at it later on. And you can see the corners are much more, well, they're more defined than in here or here. So if you look at the 170 degree one over here, that's done with the ceramic mold, and I think that performed the best out of all the other ones. You can see the corners, the edges are well defined. It has been drawn into all these pockets as well, and there are no piercing, there's no webbing here, and so we'll have a look at some questions in the next few slides. So over here you can see the molds next to the shapes we made at 170 degrees Celsius, and at this temperature both the molds did better than the other temperatures. So the first question is, describe and sketch manufacturing faults. So we have taken the high density mold because this one produced most of the faults, and most of it was webbing, and you can see over here, and that's zoomed in, and that's a side view. Webbing happens when you have extra material and there's nowhere for it to go, and we'll have a look at how it's caused and how to avoid it. You can see webbing over here as well, that's on the corner, and but at 170 degrees Celsius, that's this one, our first forming, we couldn't see the distinct features to the mold. And at 180 degrees Celsius, that's when you had the sheet being pierced, and the forming did not complete well because there was no vacuum. So the second question is, note the thinning for regions of deep drawing. Measure distance between marked squares, estimate the material thickness. So if you remember the squares we drew, 60 by 60 millimeters, they have deformed. Depending on from the side you consider, some of the distances remain the same. It's either the breadth or the length. But areas of deep draw, the length or the breadth, considering which direction you take, has changed. They have elongated. So we can measure this new length or breadth using a piece of paper or a string. I have used a post-it note, and I found it to be 75 millimeters. So we are not adding any new material in, or we are not removing any material from it as well. So the volume should stay the same. So the volume before should be equal to the volume after. So using the original measurements, the volume before can be calculated. This is before forming. So length we know, and the breadth we know, 60 by 60, and the thickness, which is h before, is 1 millimeter. So our volume before forming is 3600 millimeter cube. So now to calculate the volume after forming, we have a new measurement, 75 millimeters, and into 60, and the new thickness we don't know, so we're going to call it x, and we can solve for x. And I've done that here, and our new thickness is 0.8 millimeters. But you should remember, this is the thickness for the square we selected, not the whole sheet. So if there are areas where they have been drawn deeper, or there are shallow areas, the thickness can differ. So the third question is, describe your finished product, include a commentary on any defects. We have already done this before in question number 1 and in the results comparison. So the fourth question is, note the temperature at which you molded the material. So the first forming we did at 150 degrees Celsius, and the second one was 180 degrees Celsius, and then we came back to 170 degrees Celsius for the high density form mold, and then we did another one with the ceramic mold at 170 degrees Celsius. Question number 5 is, state whether this was a good temperature. Explain why you believe it to be so. If you answered no, nominate a better temperature for this material and explain how it would improve matters. So 180 degrees Celsius was too warm. It stretched the material, and it became too thin, and the sheet actually pierced, and it did not form well. And also at high temperatures you could see bubbling. That's like small blisters forming. 150 degrees Celsius was not warm enough. The material did not form well, and the features were not distinct, and the end product was not faithful to the mold, so it did not look like it. At 170 degrees Celsius it performed fairly well. There were some faults, but so this temperature was the optimum in terms of malleability and formability for this particular material and this particular mold. So question number 6. Describe how well the mold performed and suggest any improvements you would consider. The high density form mold, the major problem was webbing. So webbing happens because we have extra material and there's no place for it to go. So one of the workarounds is introduce dummy blocks like the ones you can see here, like that. So they will use up the extra material and reduce webbing, especially around corners. We could also introduce draft triangles to help the material flow well, and also to reduce the webbing that happened around this area, we could make the two features of the mold further apart, and if possible we could reduce the depth over here as well and over here to stop it from piercing like we saw in the 180 degree one. We could also try using a female mold as well. We could also fix wires between parts and also introduce some form of a frame to force down the material. And we could also look at using a thinner sheet as well. List 5 positive aspects of vacuum forming. It is a very cost-effective process, and it's also simple. Because it's a simple process, it can be easily taught, as you've seen in this video. It's got more design flexibility because the tooling cost is very low. You can make tools out of high density form and using a CNC mill. We could also use clay or an existing product as well. It has a low operating cost, especially with the sheets. They're very cheap. It is more precise to design specifications, so if you are producing multiple parts, it can be done easily. This machine is not suitable for mass production, but there are other machines out there which can be used for higher volumes. List 5 restrictions of vacuum forming. It's difficult to achieve uniform wall thickness throughout the object you are forming. Deeper parts are difficult to form, and it is restricted to simple parts. It is also prone to force such as webbing, like we've seen, and also chill marks, like over here, and also bubbling at high temperatures. It also has longer production times, especially for the machines we have used, but there are other machines out there, especially if you look at cup forming, thermoforming of cups. List 5 characteristics of parts suitable to be formed by vacuum forming. Simple shapes, nothing too deep because of thinning. Low cost products like packaging and single use parts. For example, like over here, tablet packaging, you're going to use it only once and you're going to throw it away. So it should be an inexpensive manufacturing process. Otherwise, the cost of the product is going to go up. If you want multiple identical parts, vacuum forming can produce precise parts over and over again. So that's it for this session. So if you have any doubts, please do contact the module tutor or the lab demonstrator. I'm going to leave you with some vacuum forming videos I made whilst doing this lab.